In this video, we're going to consider systems with acceleration. And there's two types of acceleration we'll be considering in this class: linear acceleration and solid body rotation. So first of all, a quick look at linear acceleration. Now there isn't any new theory to develop here. We kept our development of the basic hydrostatic equation general enough that it'll apply for linear acceleration as well. We just need to point out that this acceleration is no longer zero. And for linear acceleration, that is a uniform acceleration. And what I mean by uniform acceleration is that all points in the fluid have exactly the same acceleration. So same magnitude and same direction. So that's the end of the theory for linear acceleration. We'll see when we do examples how this plays out. But the basic difference is that's no longer zero, but it is a constant. By that I mean the same at all points in the fluid. So this is a situation where the entire container and the fluid it contains is accelerating off in a straight line in some direction. So if you had a tanker truck and it was pulling away from a red light, the fluid in the tank is accelerating in a straight line all at the same time. Now the second situation where acceleration is important is rigid body rotation. And this is a little more complicated because the acceleration is not the same everywhere in the fluid. Now we still have our same basic hydrostatic equation. We don't need to make any changes to it. It's valid for all of these situations. As long as the fluid is in the hydrostatic state, then this equation is valid. And remember, hydrostatic state means that no 2 points in the fluid are moving relative to each other. Well, a fluid undergoing rigid body rotation still satisfies that condition. No 2 points in the fluid are moving relative to each other. Now, in rigid body rotation, however, this acceleration is no longer a constant, but it depends on where we are in the fluid. So for rigid body rotation, that acceleration will be a centripetal acceleration. And centripetal means directed towards the axis of rotation, or towards the center of rotation. So let's illustrate this with a little sketch. So here we have a container of fluid. It might be a cylindrical container. It doesn't really matter what the shape of the container is. But the important thing is this vertical axis Z here, this container is rotating around that axis. So rather than using a Cartesian XY coordinate system, these types of problems are a lot simpler to describe using a cylindrical coordinate system. So that's what we're seeing here. We have an axis of rotation, which we're calling Z, but the other coordinate that we have here is a radial coordinate. So that's the distance away from the axis of rotation, R. So this is an RZ coordinate system. Now, this is the fluid that we're studying. We still have gravity at play here, and G is still projected straight down, so it's in the negative Z direction. But now, if this whole fluid is rotating, then the points of this fluid, because they're rotating, they're accelerating towards the axis of rotation. That's a centripetal acceleration. And what is that acceleration? What is the expression for A that we need to substitute into our basic hydrostatic equation? Well, it's minus omega squared R. And the minus is there because the acceleration is in the opposite direction to R. So if we take a point in the fluid right here, then this vector would be R, and it has some magnitude and its direction is directed away from the center like that. Well, the acceleration of that fluid is in the opposite direction of that. It's a centripetal acceleration, accelerating towards the axis of rotation. So that's why there's a negative there. And the magnitude of that acceleration is omega squared R. And so omega is the angular speed of this. So that would be in radians per second, the rotation rate. So notice that the key thing here is that the acceleration, this acceleration that the fluid is undergoing, is different at different places in this fluid because they're different distance away from the axis of rotation. So acceleration is now a function of position. It's not a constant like it is for linear acceleration. So moving on here, let's give this fluid some angular velocity now, omega, so some rotation rate omega, and take a look at the pressure gradient vector. So this is our basic hydrostatic equation. The difference now is we cannot cross this term off because this fluid is in solid body rotation. So what we'll do is substitute in for g and acceleration for this scenario. So we have our pressure gradient, rho g still, just distributed the rho in here, but we're substituting in for the acceleration this expression for centripetal acceleration. So notice this negative and this negative have caused a positive to occur here when we combine those together. And again, we've distributed rho in here. So the pressure gradient now has these two components. This component is a constant. That doesn't change as we move to different places in the fluid, but this component is a variable. It does change as we move to different places in the fluid. Now, similar to what we did for a Cartesian coordinate system where we used I, j, and k as unit vectors, here we want to define r hat as a unit vector in the r direction. So we can split this r vector up into a magnitude and a direction in the next step here. So that's what we've done here. So I've expanded the vector gradient operator here to explicitly show the two components. So we have a radial component to the pressure gradient, partial p, partial r in our r hat direction, and we have an axial component to the pressure gradient, partial p, partial z in the k hat direction. So that's just expanding this out and showing the two components of it explicitly. On the right hand side, our g vector is in the minus k hat direction. So this becomes minus rho g k hat. And then here all we've done is replaced this position vector with its magnitude r and its direction r hat. So notice the left-hand side of this has an r hat component and the right-hand side has an r hat component. The left side has a k hat component and the right side has a k hat component. So this is really two scalar equations written as a single vector equation. Now what we want to do is take a look in a little more detail at this pressure gradient vector. So we're just going to make a little bit of room here. That's the same equation repeated at the top of the screen. So if we take a look at this pressure gradient vector, so we're just going into a little spot in the fluid anywhere, and I'm just drawing it over here where I have more room. This whole sketch that I'm gonna do here should really be done in the fluid, but I'm just doing it over here where there's a little more room. So this is our pressure gradient vector. And we need to realize that in this coordinate system, it has two components. So it has a vertical component and a horizontal, or a z component and a radial component. And we can look at this expression and see that this component is minus rho g. So minus rho g is our k component, or our vertical component. And the radial component is rho omega squared r. So that's coming right from there. So this pressure gradient vector has a k component and an r component. Now, the important thing to realize is as we move around in this fluid, we move to different locations in the fluid. This part doesn't change. Those presumably are constant. The density of the fluid and the acceleration of gravity are constant everywhere in that fluid. So the vertical component of this pressure gradient vector doesn't change as we move from place to place. However, notice the radial component does change as we move from place to place because of this. The rho and the omega are constant, but as we move around in this fluid, our r coordinate, or our distance from the axis of rotation, is changing. So that means for this fluid, as we move from place to place in this fluid, the direction of this vector changes. It points in different directions as we move around in that fluid. So what's going to happen here is we're going to have lines of constant pressure that are no longer straight. They're curved. And it turns out they're going to be parabolic. So if we look back in our container here, a line of constant pressure is going to look like this. So once this container is spinning and the fluid has reached a hydrostatic state again, in other words, it's in solid body rotation, that free surface, which started off as flat, is going to become parabolic. And in examples, we'll show that this is actually a parabola, that z is a function of r squared, is the equation that describes that surface. But let's just take a look at a few spots. Right on the center line here, notice that our pressure gradient vector is pointing straight down. So our del P vector on the center line is pointing straight down. Remember, the pressure gradient vector is always perpendicular to a line of constant pressure. And this free surface is a line of constant pressure, happens to be atmospheric pressure. So back here, this is a line of constant pressure. This is our pressure gradient. Those are always at right angles to each other. So on the center line, R is 0. So the length or the size of this component is shrunk down to 0. So the pressure gradient vector on the center line is pointing straight down. At any other location on this free surface, the pressure gradient vector is going to have a larger and larger and larger horizontal component. So it's always perpendicular to the surface, and because its horizontal component is growing with r, the horizontal component of that pressure gradient vector is increasing, and the free surface slope has to become larger and larger and larger as we go further and further away from the axis of rotation. Now, this particular line of constant pressure happens to be atmospheric pressure because that's the free surface, but realize we can go anywhere in this fluid and define the pressure gradient vector as well. So as we go deeper down into the fluid, we'll see that all of the lines of constant pressure have this parabolic shape. They're just shifted down further and further to higher and higher and higher values of pressure. So remember, this thing is still rotating around this axis. And so the maximum pressure in this container while it's undergoing solid body rotation is going to be down in these corners. This is the same corner. Remember, it's a cylindrical can rotating around that axis. So these are really the same location. Why do I say that's the maximum pressure? Well, because to get to that point, you need to cross a maximum number of lines of constant pressure. Remember, each of these lines is a line of constant pressure. If we were to say that the contour interval here is 10 kPa, then the pressure here is 0, the pressure there is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. So the pressure down in this corner is maybe 150 kPa in that little illustration. So you can tell just by looking at these lines of constant pressure where the maximum pressure is going to be. And it's going to be down in that bottom corner because we're at maximum depth and at maximum radius or maximum distance away from the axis of rotation. Now, the first lab that you're going to do in this course, you're going to see this in action. We have a transparent container with water on a turntable, and we set this up in solid body rotation, and you'll make some measurements of this free surface and compare it to the theory that we've talked about here in this lecture. So you will see this in action in the first laboratory in the course. So that's the final lecture video in this module. There are example videos as well that you should be viewing, but we'll see you in those example videos. Bye for now.